Hello, good morning. In the last class, we have been discussing about non-uniform grid. For example, if we have to solve Laplace equation or Poisson equation inside a circle with say Dirichlet or Neumann boundary conditions. So, then when we discretize, so definitely when we consider the boundary points, what would happen when we fit a standard 5-point formula. So, the boundary points will be slightly skewed towards inside. Okay. So, you would expect non-uniform mesh sizes. Okay. So, let us solve a problem and try to see how we can handle this. Okay. So, it is 2D case. So, in the first quadrant, u is 2 on x equal to 0. So, this we started in fact in the last lecture. Okay. So, when we discretize, I have already mentioned so, for example, this is uniform. Okay. Then suppose we discretize. Okay. So, then if you consider this as u I j, so then these two are having equal length and these two are having equal length. However, so the step sizes are non-uniform. So, we cannot use our regular technique. So, we have to come up with a slightly modified technique. Okay. So, we will address this. So, now I draw this and so this is a point say S Q P A and B, and we this is H1 and this is H2 and H3 H4. Okay. So, now if we take the normal through Q, it goes like that, and if we take the normal through P, it goes like that. Okay. So, now these points, so this point we call N and this point we call M. Okay. So, now we have to see we can compute these points, but when we run the standard 5-point here, it expects this and this. Okay. So, how do we handle? Okay. So, recall the formula. So, in this case H1 is H2 and H3 is H4, and the formula which we got u at, so this is u x I x j y j plus UQ plus UP plus UA plus for Laplacian with this irregular grid from the general equation which we have discussed in the last class. So, we can arrive at this. So, UQ, UP, UA and UB are involved. Okay. So, this is a now for the case of H1 equal to H2, H3 equal to H4. Okay. So, let us simplify this. So, this is our equation. However, the original problem which we defined, we have the normal prescribed. Okay. So, we have to compute. So, this is our Q, this is P. So, we have to compute dou u by dou n in terms of these values. Okay. So, we can do that. So, dou u by dou n at q can be written as u q minus u n by q n. Of course, this is up to first order. So, what is happening here? So, this is q and this is n. So, dou u by dou n at q is u q minus u n by the distance, then p u p minus u m by p m So, this is P and this point is M. So, the normal is given. Similarly, one can compute the value u n as follows. So, we need to draw this again and again. Okay. So, then u n is given by, so this point is S. So, u n is S n u b plus b n u s by H 4. So, this is a interpolation. So, let me, so this arm is H 1, this arm is H 2, this arm is H3 and this arm is. So, these arms are H1 is equal to H2, H3 equal to H4. Okay. So, now this is a by usual interpolation. Then similarly, um here will be Sm into ub. So, this is A and B plus Sm into ua plus Am into Us by H3, because Sm into Us plus Am into Us by H3. Okay. So, now these values, so we have computed in terms of the existing grid points, the derivatives. Okay. So, that since the derivative boundary condition is prescribed, so we can explicitly get algebraic equation. Okay. So, now using this is the Neumann data. Okay. So, when we use Neumann data, we have, so this is both at P and Q. Okay. And we have computed earlier the normal at P and Q. Moreover, we have computed u and um via interpolation. Okay. So, now we combine this, So, combining uq minus un by qn, this is equals to x square minus y square at q. So, this implies uq minus un we have computed at q. Similarly, we get up minus um by pm. So, this implies okay. And we have u equals to 0, u equals to 2 on x equals to 0, y equals to 0. So, this implies u a is 2 and u b is 2, because both are on the axis. So, therefore, u q minus, so from the earlier one u b is 2. Okay. So, we use that value. So, u q and the second one u p minus 2 S m Okay. So, we have got explicit algebraic equations. So, now we have to compute these distances, which distances q n p m. Okay. So, let us proceed as follows. So, this is slightly algebra routine calculation. So, from the figure, this is q p n m. Now, this is A and B. So, therefore, tan pi by 6 is N B by O B. Okay. N B by O B. So, this implies N B is similarly A m is. So, you can compute, then also S q equals to P s equals to. So, this you can compute. So, therefore, this is our S. So, therefore, H 1 and H 3. Okay. So, these are straightforward. S q, P s, these are equal. Okay. So, this is H 1, then similarly S b and A s, H 3 and H 4, they are half. Okay. So, we have points Q is and P is P and Q. So, accordingly Q 1 is and P m is right. So, now the formula, the algebraic equation simplifies to So, I am giving the crude calculation, but you can simplify. Okay. Then further this can be simplified to the other two equations U p is to So, this is one equation, and similarly U q So, you can simplify, and moreover this can be simplified Okay. So, now we have UP, UQ, US. So, 3 equations and 3 unknowns. So, let me put them. So, from these one can obtain, for example, I have solved. So, you may also try. Okay. So, when we have Neumann data equals to given, what is the Cauchy data? Cauchy data is u have to be obtained, and this is what we have obtained, the value of u. Okay. So, this is the case where you have the grid non-uniform grid, and you have to interpolate and also approximate the derivative, and then obtain the corresponding boundary data, because we have Neumann data given, therefore, the corresponding Dirichlet data we obtain. Okay. So, now let us see in cylindrical coordinates how the corresponding discretization works out. So, Laplace equation axisymmetric cylindrical coordinates. Okay. Accordingly, the operator becomes, the corresponding equation so remember I have considered axisymmetric. So, the dimension has been reduced by 1, otherwise we have standard r phi z cylindrical, but because it is axisymmetric these are independent of phi. So, now say in a domain okay. So, now we need the corresponding boundary conditions. Say this is f of r, h of r, then u r z z of z, and say here the derivative okay. So, now we have to discretize, discretizing the domain. R L is L H, then Z M is M K. Okay. So, then So, when we have this kind of discretization, it is like okay. So, this kind of discretization so R 0 to R has been discretized as LH. So, L equals to 1, L equals to 2 okay, in this direction. Okay. So, that means L values we should literally take from -1 to 1 when we say L 2 -2 to 2. Okay. So, like that, right. So, now what kind of approximation we use? So, this we discretize plus of course error. So, we approximate. So, then expand the Taylor series expansion and then collect the coefficients and compare. So, by doing so we get the following system. So, please do yourself and make sure that this system is obtained. Okay. So, now when you remember RL is LH and Zm is Mk. So, then let us have this M SH, that means K is taken as SH, okay, special case. So, then in this the equation reduces to the discretized equation reduces to so assuming f is function of u as well. So, now this is the equation discretized version. However, as r goes to 0, so the differential equation becomes okay, as r goes to 0, the differential equation reduced to this. Now, corresponding discretized version corresponding to this, the discretized equation however, this is as r goes to 0. So, therefore, this is for L equals to 0. So, this is important. Okay. Now, we have dou u by dou r equals to 0 at r equals to 0. So, this implies the fictitious value can be eliminated, because when L equals to 0 we have a fictitious value from here. So, this can be eliminated. So, 1, 2, 3. So, with this one can obtain the solution. Okay. So, let us see at least for a simple case the discretization and the system of equations. Say we want to solve this. U is 0 in the boundary and say h equals to k equals to half. Okay. So, this gives R L equals to L by 2, Z m equals to m by 2, and L okay. So, therefore, the boundary conditions U L 2 equals to 0, U 2 m equals to 0. This is for L 0 1 2, because you can see h equal to k equals to half. Okay. So, from 0 to r 0 to 1. So, therefore, we have only r 0 to 1. So, that means we are so half. So, this is 0 and this is 1. Okay, I mean I should have drawn better. So, this is half. Okay. And z planes. So, z planes also k is half. Okay. So, we have to correspondingly we have to discretize. Okay. So, therefore, u L 2 is 0, u 2 m is 0. Okay. So, these are the boundary conditions. So, then if we recall, so we have these equations. Okay. So, we have to run these equations at points. So, since z is minus 1 to 1, so the points involved are 0 0, half 0, 0 half, half half. Okay. So, at these points we have to run the equation. Okay. So, this equation we have to run. So, for example, at 0 0, then half 0, so again at the remaining points, these 2 points we run and then we get a algebraic system. So, this gives some idea of discretizing cylindrical polar coordinates. Of course, not arbitrary case, we have considered axisymmetric case. Okay. So, let us try now on stability aspects of these discretizations. Okay. So, let us check the stability aspects. Okay. Accuracy and stability. Okay. So, these standard 5-point methods are discretized and the error is of the form u of x I minus 1 y j u of x I plus 1 y j plus u of x I y j plus 1 plus u of x I y j minus 1 minus 4. Okay. If it is Laplacian and then if you have a non-homogeneous, we have an f. So, this is the error. Okay. So, when we expand and then see, this reduces to okay. And correspondingly, if we introduce then error satisfies the following equation. Error satisfies AH for a particular step size. So, where A has a specific structure. So, AH has the specific structure. Where T also has a specific structure. So, this we have written before. So, I am not putting completely. Okay. So, now for stability of the method, we need the following. For the method to be stable with respect to any norm, suitable norm. So, this is uniformly bounded as h goes to 0. Okay. So, now let us see corresponding to the matrix A, just now we have defined the pk eigenvector UPK, this has m square elements, okay, given by so corresponding to this matrix, the pk eigenvector, this has m square elements, okay, and the corresponding eigenvalue is lambda pk, okay. So, lambda 1 1 for example is which is close to 0, okay. And if you go for the spectral radius of this, we have okay. So, this condition is satisfied. So, therefore, stable, the method is stable. So, this is a general check for the stability of this method. Okay. So, in the last class we started a problem on discretization with respect to polar coordinates. So, let us see because we are almost concluding the elliptic equations. So, let us see this problem and try to finish this. Okay. So, in the circular case, so we are solving this and the corresponding approximated this term, then and this gets simplified. This gets simplified to this form. So, let us introduce some notation. So, this is of the form where okay. Now, let us say we consider a problem So, we would like to solve. So, this is I equals to 0, I is 1, I is 2, I is 3, then j 0, j 1, j 2. So, let us say we have u of r 0 is 1 and say this is pi by 4. So, u of r pi by 4 is minus 1 and say this boundary is u of 3 theta equals to 2. Okay. So, that means our domain is this. So, if this is a domain and these boundary data is given, so we have unknowns, only 2 of them. Okay. So, let us say we want to run I equals to 1, j equals 1, this equation. Okay. So, this if we run equation here I equals to 1, j equals to 1, it will ask, you see I equals to 1, j equals to 1. So, it will ask 2 points here, 2 points there, right. So, we get of course corresponding to, so I equals to 1. So, a I is half, a I is half, u 0 1 corresponding to this plus b I is half, I is 1. So, this is 3 by 2 and u 2 1 plus, so c with minus I am sorry minus 2 1 plus. So, for these let us, if this is pi by 4 and corresponding to j equals to 1, what is k? So, this gives theta equals to pi by 8. Okay. So, assuming k is half. Okay. So, the discretization, so maybe we can have a quick recall. So, r equals to I h, then theta equals to j k, right, and what is step size. So, here h is taken as 1 because I have given this is r equals to 3. Okay. So, this line r equals to 3, accordingly I have given, but whereas this line theta equals to pi by 8, that means k is half. Okay. So, pi by 8, then yeah, okay. So, this is okay. So, now we get, just let me recall, this is, yeah, okay. So, this is pi by 4, half of it, okay, yeah. So, this will be 64 by pi square u11 plus u12 plus u10, because DIEI. So, this is coming to be I is 1, right, and h is 1. So, we get then I is 2, j is 1. So, again we compute the coefficients. So, this will be 3 by 4 u11 plus I is 2. So, 5 by 4 u31 and this will be u21 okay. And we know these are the points unknowns u11 and u21. Okay. So, what are the unknowns? u11, u21, u11, u21, and we remaining we substitute from the boundary data, okay, and solve for, okay. So, this gives some idea how to discretize and obtain the solution. So, you can take maybe 2 points if you take one more line. Okay. So, for example, the number of grid points increases. Suppose somebody takes the domain, suppose you restrict your domain to be this. So, you are solving, so that means this is given, u is given and u is given. So, what will be the grid points where you have to seek the solution? So, these are the 4 points we have to seek the solution. Okay. So, I is 0 and this I1, I2 and I3, and here J0, J1, J2, J3. Okay. So, these are the grid points. So, we can extend, suppose if we solve and depends how many. So, accordingly the grid points will be increased. You see, these are the grid points. Okay. So, this is a general idea of how Laplace and Poisson equations are solved. So, in general for any elliptic equations, if you want to approximate using finite difference methods, we adopt this, and if you consider the standard 5-point formula, you can refer some literature where if you look at your Laplace equation, it is invariant under rotation. So, if you rotate, so then you get a slightly different version Okay. So, I would like to show you because many books refer that. So, this is I j and your diagonal is asking I plus 1 j, I minus 1 j, I j plus 1, I j minus 1. So, this is u I j. Okay. So, if you rotate by 45 degree, then it should expect something here, something here and something here and something here. Okay. So, this formula is diagonal 5 point. So, diagonal 5 point formula. So, this is very much exists in literature. So, you can refer and try to solve a particular problem using this method and this method. And compare how this method works out. Okay. So, with this we are almost done with the elliptic PDEs. So, from the next lecture we move on to hyperbolic PDEs. Until then, bye.